Hello, everyone. From today, we are going to start learning about electromagnetism. And in our today's first lecture on this topic, we will learn about magnetic fields, magnetic field lines, and the interaction of magnetic fields. In other words, that a magnetic force on a current carrying wire or on a charged particle. So let's start with understanding the concept of magnetic field. We know about magnetic bars, that if, for example, we have a magnetic bar and it will actually fill a space around it in which you can experience magnetic force. So that what we can say that it is the magnetic field of that bar magnet. Very first time Faraday, he did a simple experiment. He used a bar magnet and sprinkled some iron, very small particles that we call iron flings around this bar magnet. And then he observed this kind of a picture here that shows that the alignment of that iron particles around this bar magnet. So with this picture, we developed an understanding of a magnetic field, that this magnetic field can be represented with magnetic field lines. And these magnetic field lines, in fact, are imaginary lines. These are not real lines, but they actually play a very important role to understand magnetic fields. For an example, that if we do have a bar magnet, then these magnetic field lines, they start from one pole, that we call it a north pole of a magnetic field, and that ends at the other pole, which is a south pole. So direction of magnetic field lines is always from north pole to south pole. The second thing is that it is actually always in the form of a loop. Loop means that it will actually start and it will also terminate. So it will be actually making a one simple loop. So then the second thing is that if, for example, here you can also see it is like an experiment where you have a bar magnet and you are using a compass to actually identify these lines, particularly the direction of these lines. So second thing that we can learn from these lines is intensity of the magnetic field. For an example, that if we have magnetic field lines and that are very close to each other, and they are actually also at the same distance from each other, then you can say that this magnetic field is stronger and uniform. And for example, when I say it is stronger, then it means that compared to the other space where the magnetic field lines are far away from each other, means that the density of the magnetic field is actually lower, meaning that the number of lines per unit area, number of lines per unit area is lower, and this unit area is the cross-sectional area. So then here in the second picture here, the strength of the magnetic field is lower compared to the first one. But if we look both of these pictures, magnetic field is uniform. What if, for example, we actually write more lines around this bar magnet, then this next line, it will be somewhat like this around this bar magnet, you can see from the bar magnet, the very first line is at this distance, then the distance between the next two lines is increasing, and the next lines is also increasing. So this magnetic field around a bar magnet is non-uniform, non-uniform. It is not actually a uniform field around the bar magnet. And secondly, you can say closer to the bar, the magnetic field is stronger. And as you go far away from the bar, magnetic field strength reduces. And the second thing which I would like to make clear here, that is the magnetic field flux. So flux, you could understand that this is actually, you can say, the number of lines that are passing through some area. So for example, these are the magnetic field lines and that are passing this cross-sectional area, then your magnetic flux phi will be equal to the magnetic flux density. B is magnetic flux density times this cross-sectional area. So this phi is magnetic flux and B is flux density. Flux density. So you can very easily also understand from this formula that our flux density B is equal to flux over A, meaning that flux per unit area. So B is our magnetic flux density and phi is our magnetic flux. We also know that the magnetic field, and I'm pretty much sure that you already have experienced this even in your childhood when you were you got an opportunity to play with magnetic fields, that if you do have two bar magnets, they also can attract and repel. And the reason is that the north pole that attracts the south pole, meaning opposite poles, always attract, but the similar poles, they repel each other. And this you could also understand with the concept of the magnetic field lines, because this magnetic field lines is going like this, and from the other bar it is actually also, you can see, facing each other, they are repelling. But in case of from north to south, the line will start from the north and it will terminate at the south. So there is actually the interaction, and that is the attractive interaction when the north and south are face to face, but the similar poles, they repel each other. So here we understood about the magnetic field and magnetic field lines, that how we can understand the properties of magnetic field using the concept of magnetic field lines. And the magnetic field is not only from magnetic materials, but we can also observe the magnetic field if, for example, we have a conducting wire, and in this conducting wire, a current I is flowing, like, for example, from bottom to up, meaning the upwards. And in this case, what will happen, that this flow of the current in this conducting wire will develop magnetic field around this current carrying wire. So what is happening here, that the flow of the current is developing the magnetic field, and this magnetic field can change its direction with the change in the direction of the current. And the magnetic field direction in a current carrying wire can be determined using the concept of a right hand rule. What the right hand rule is, that use your right hand and then put the thumb along the direction of the current and curl of the fingers will give you direction of your magnetic field. For an example, in this picture, current is going up, and then our actually this field is anti-clockwise around this wire. And if you switch your current downwards, then what will happen that you can also experience with your hand, that this actually magnetic field will also switch and it will go clockwise. So it means that what is going on, that when there is a flow of a current through a wire, of course a metallic wire, a magnetic field generates around the wire, and the direction of that magnetic field depends on the direction of the current. So this magnetic field direction can be identified by using the right hand rule. Remember, for the right hand rule, that there are two things: number one, thumb, and number two, the curl of the finger. So it means we are actually testing two parameters, and here in this example, current and magnetic field. So let's consider that if we turn this wire in the form of a coil, so then what will happen to the magnetic field? So magnetic field will be like this. Let's understand it here. So for an example, that we do have now a coil, and this coil, you can understand that you are just turning your wire in this way to developing a coil. So here in this picture, we have a half cross section of this coil, meaning that this wires, this part is actually behind this, and here it is actually cut, and then here it is again going inside there, going inside there, going inside there. There is the flow of current. Let's understand the direction of the current in this case. So here you can see cross. The cross means the current is inwards the screen, and here we have a dot, that means the current is coming out. To remember this, just remember an example of an arrow. For example, this is the head of an arrow, and here we have a tail of the arrow. If, for example, we are at the front of it, meaning that this arrow is coming towards us, then what would we observe? We will observe the tip of the arrow. So it means the vector is coming towards you. But if, for example, you are observing this arrow from the back, then you would see the wings of this arrow. That means you would actually observe the cross of this arrow. So this means that the vector is coming out of screen, meaning towards you, and this means the vector is into the screen, meaning it is going away from you. Now let's understand the development of the magnetic field in case of a coil. So first we try to understand the field at the lower part of this wire. So here the current is inwards. Now put the thumb of your right hand towards this screen, then you will see that the curl of your fingers is clockwise like this. So then we will have magnetic field lines clockwise around this part of the wire. Now this current is going here, and from the upper part of this coil, the current is coming out. Now put your thumb towards you and see what happens. The curl of the fingers, then you would see that this is anti-clockwise over here. Now, similarly, this is actually happening to the all parts of this coil, meaning that to every turn of the wire in the coil. So in the result, what would happen? That here, if we look in between these two turns of the coil, that here the magnetic field is downwards and here magnetic field is upwards. It means here the field lines are cancelling each other. The field lines are cancelling each other between these two wires. So then we have no field between these two wires. And what if, for example, we go little more above, then this field line will actually have the same, you could say, the direction, the other field line, so they will combine together. So here outside the coil, we do have a field, but this field will be non-uniform because you can see the other line is far away. So this field outside the coil is non-uniform, non-uniform and weaker. What happens inside the coil? Let's have a look. Now, as we actually see the formation of magnetic field lines outside, in the same way you can see the direction of the magnetic field inside the coil from the first turn and from the second turn. They are actually along the same direction, so they will combine together and they will develop the line from, in this example, it is from left to right. Now, if you see to the lower part of this coil, you can also see that the magnetic field lines from one turn to the other are in the same direction and they will come together and combine a one magnetic field line. So it means that from both sides of the coil, upper side and the lower side, the magnetic field lines are in the same direction. And in this picture, that direction is from left to right. And secondly, you can also observe that the field within the coil is uniform and also stronger because we do have the higher intensity of the flux, meaning there are more lines over a unit cross-sectional area inside this coil. So now we can also use our right hand rule to check the direction of the magnetic field in the coil. So in the right hand rule, what we actually see that there are two parameters. There are two parameters that are involved to check. And here again, there are two parameters. Number one is the magnetic flux density. The second is the flow of current in the coil. In our previous example of a straight wire where a current was actually along a straight line and magnetic field was actually in a circular form, meaning it was the curl. What here, the current is actually circling. So it means that this time we will curl the fingers of a right hand along the curl of the current, and the thumb will indicate will indicate direction of the magnetic field. Now you can use your right hand and put the fingers toward this screen and curl them, because current here is going to the screen and coming out from the screen at this point. So then you will actually curl the fingers of your right hand. They go toward the screen and coming out. So thumb, you will find it is towards the right. So this is the way of identifying the magnetic field direction in a coil. And here, the another important point is that between the wires, magnetic field is canceling, and outside it is non-uniform and weaker. Inside it is uniform and stronger. So mainly the field of a coil is inside the coil. So here, this is our understanding of the field of the coil. Now we move ahead and we try to understand that if we have a constant magnetic field and we put a wire inside the magnetic field, and that wire, it carries current, meaning that the current is flowing through the wire. What would happen in this case? Let's try to understand it. So very first thing that you would understand that, for example, from this picture, we do have a bar magnet, and from one side we have a south, and from the other side we have a north, and magnetic field lines will be from north towards south. And here let's see that our current from this in this wire is flowing along this direction. So you can understand with our previous understanding that here actually we have two magnetic fields. We have two magnetic fields. One is actually because of this bar magnet, which is a constant field. This is a constant field, and this field is because of the bar magnet. Secondly, when there is the flow of current through this wire, then of course what will happen, we will also have a magnetic field around this current carrying wire. So there are no two fields, and they will interact with each other. When they interact with each other, then a magnetic force generates because same poles can attract, and same poles, sorry, can repel, and opposite poles attract. So here what is happening, that if we have this situation, the force is generated. Very first thing, let's discuss the direction of that force, the force of magnetic field. So we would say that actually this constant field, the field of the bar magnets, is applying the force on a current carrying wire, and that force can be found using left hand rule. What the left hand rule is? Now take your left hand, put the very first finger of your left hand along the direction of this magnetic field, and the second finger, it should be along the current. Now you can see that your first finger and second finger are at 90 degrees to each other. Where is your thumb? Thumb is upwards. So this is our magnetic force FB towards up. Now you can also actually see that if, for example, that in this wire, if you will switch the direction of the current, then now check from your left hand, if you switch the direction of your second finger, then thumb will go down. And now keep your current here, then switch your active direction of the magnetic field, meaning that this south is the north now and north is the south. Then you can see that what is going on, that your thumb will go up again, and this means change in the direction of the current, or the change in direction of magnetic field will change the direction of the magnetic field. If you are changing both, then your magnetic force will remain along the same direction, because you are changing both parameters. And before going to understand mathematics of magnetic force, let's visualize this force, that what is going on. Now here we have a permanent magnet because of the north and the south pole of a magnet. And between these poles, we have magnetic field and we have a wire, and the current is going into the screen here. So if it is going into the screen, so we use the right hand to find the direction of the magnetic field around this wire, and that will be clockwise here. So here, this is a direction of magnetic field because of the bar magnet, which is from left towards right. But at this upper part, you can see here we have magnetic field because of the wire. So both fields are actually along the same direction. So they adds up. They adds up. But at the lower part of this wire, our magnetic field directions are against each other. So then they are cancelling each other. So it means the field above this wire is stronger compared to the lower part of this wire. So this is the reason that this wire will experience the force, and that will be downward force. Now, let's understand the mathematics of this magnetic force. And for this, what I do, I put a small board here, and where we will do the mathematics. Let's say we have here our blackboard, and now we write on this one. This force on a current carrying wire inside magnetic field can be found calculated using this formula, that F is equal to B I L. So F is the force vector quantity. So what the B is? So we know that B is actually the magnetic flux density. So B is a magnetic flux density. So this is magnetic flux density. And I is current, the value of current in the wire. And L, that is the length. What length is it? So this is the length which is inside magnetic field. For example, that we have magnetic field within this area and our wire is like that, then here this is the length L, which is inside magnetic field, not the total length of the wire. Now, if we see this, it actually tells us that what is going on, that the force of the magnetic field, it depends on the value of the magnetic flux density, the value of the current in amperes, and how much length of the wire is in the magnetic field. So by increasing any of these parameters, we can increase the force, or by decreasing any of these parameters, we can decrease the force. Now here we know that what current is. Current is the rate of flow of charge, meaning that it is mathematically charge divided by time. Now, if we use this relation in our first relation of the force, we can see that this force will be equal to magnetic flux density charge times length, then divided by the time. Look here, in this equation, we got length divided by time. What is it? So displacement divided by the time is velocity. So length divided by time is velocity. Now, this force of the magnetic field F is equal to BQ times velocity. So I'm trying only to give you the very simple mathematics just to understand the concept of magnetic force on a current carrying wire. So now we can see that this force, it actually depends on the magnetic flux density, the value of the charge, and the velocity of the charge. Okay, so to go into more details, before this, let's raise a question that for an example, that there is some angle between magnetic field and the current, and if we have magnetic field along this direction and the current is not exactly perpendicular through this magnetic field or inside this magnetic field, the current direction is, let's say, like this, and we do have some angle theta between the current and magnetic field B here. Now you can see that actually this here, in this relation, our magnetic field and current, they are perpendicular. So it means that we need to use a perpendicular component of the current, and this perpendicular component of the current is I sin theta. So what does it mean? That if there is an angle between the current and magnetic field, then we will add in this formula sin theta. So our formula will be force is equal to magnetic flux density, current, length of the wire times sin theta. And similarly, we will also have that in this relation. What if this theta is equal to 90 degrees, then our formula will be at max. F is equal to BQV. This is our actually equation of the force of the magnetic field on a current carrying wire. Now, let's understand little more physics of this force using this formula. Okay, so what formula we got so far? We said our formula will be F is equal to magnetic flux density, value of the charge, and velocity of the charge times sin theta. So here there is a very interesting thing that we need to understand, that for an example, that if this theta is equal to 0, what does this mean? This means that if magnetic field direction is like this and the current is flowing parallel to the magnetic field. Okay. Okay. In other words, if we have magnetic field like this and there is a charge particle, and this charge particle Q is moving parallel to the magnetic field, then magnetic field cannot apply any force on such a charged particle. So if charge particle is moving parallel to the magnetic fields, then you can say magnetic field is blind. So charge particle can pass by unaffected. So this theta should not be 0 to experience any force from magnetic field. Second thing is actually from this point, the velocity. You see, if for example, I have some magnetic field and I put there, so here we have some magnetic field and I put a charge particle Q here with its velocity 0, meaning that this charge particle at rest, then in that case again our force will be 0. So magnetic force on this charge particle which is at rest will be 0. If it's moving parallel, it is 0. Now, what we understand here, that to experience the force from a charged particle, the particle must not be moving parallel to magnetic field lines. One thing. Second, it must not be at rest. If it is at rest or parallel, then the field will be totally blind about that charged particle. So here we can also see one more thing, that for an example, that we can say that we have a charged particle which is a simple proton. Then you can say the charge of this proton is positive E, and which is a constant value B and V. So these are two vectors, magnetic field and the velocity. And we know that it actually depends on vertical component sin theta. So you can also write it in the form of a vector product. E is equal to B cross V. Okay, so just up to this point, just understand the simple concept of magnetic field force on a current carrying wire or a moving charged particle. You see, our actually understanding starts with the current, and here we have a single charged particle. That what is happening, that if we put a charged particle in a magnetic field, the two things must be there. Number one, the charged particle must not be at rest. Secondly, it must not be parallel to the magnetic field to experience the force of magnetic field. Very good. I think up to this point, the things are clear. So now we move ahead, and here we try to do an experiment. And in this experiment, what we do have, we have a scale that measures mass. So in other words, you can say that we are measuring the weight, because mass, we can get the value here, times it with the strength of gravity, which is 9.81, we will get the weight, and it is in the units of force, Newton. And we put a bar magnet on this scale. When we put this bar magnet on this scale, we put our this mass scale at 0. We set at 0. So meaning that we have subtracted the mass of this bar magnet, and then we have a wire, and this is, let's say, is a very thick copper wire, and we have a battery. So flow of current is along this, for example, from positive and negative. So from positive towards negative. So current is flowing like this along this direction here. Okay, so this is the direction of current in this wire. And here we have a north pole, and this one is the south pole. So magnetic field lines are like this. So you can see here that the magnetic field and current are perpendicular to each other. So it means the magnetic force F is equal to BIL in this case. Very good. Now, what would happen? That here we do have this one is a variable resistor that you can change. You can change the value of current that you will be measuring using this ammeter. What will happen here? Let's understand. Now, this magnetic field will apply a force on this current carrying wire. Okay, in which direction? And for that, we will use left hand rule. First finger along the field. Okay, second finger along the current thumb, that you can see it is upwards here. So this is the force that what this bar magnet will apply on this wire. What we have clamped this wire, and we have fixed it here, and now this wire cannot move upwards, but there is a force. If there is a force and this wire cannot move up, then according to Newton's third law, there will be similar force downwards. So it means that what is going on, that this bar magnet is applying the force on this wire and wire is not moving, and then according to Newton's third law, that this force will be experienced by this bar magnet and that will be downwards. Okay, before starting this experiment, before giving current to this wire, we actually put our this scale at 0. Then now you can understand that whatever the force is there on this bar magnet, that will actually appear on the scale as the mass, meaning whatever value we will get here, we time it with the strength of gravity, and that will give us the force experienced by the bar magnet, and that actually is the force applied by this bar magnet on this wire, and this force will be equal to mg, the value that we will have here, times it with the g, then this will be equal to BIL. Now you can actually using this formula, what you can do, you can actually measure the magnetic flux density of your bar magnet, because this mass we have observed already from this scale. G is constant, I is the current that this ammeter is giving, L is the length, so length of the wire which is inside the magnetic field, so between these 2 points. So this is the L, length of the wire inside the magnetic field, that you can actually measure using some scale. Now if we look this formula, we actually also learned about uncertainty and errors in the data. So you must do multiple measurements for one current and then take the average, and then you also change the value of the current to see what happens to this force on this current carrying wire. If we look this formula, then uh, we can understand the following, that what's going on. We are changing the current, length is constant, magnetic flux density of the bar magnet is constant, G constant, and M we are measuring. So it means that mass that we are measuring here is actually our dependent variable that depends on this value of the current, that what you are changing. Now we will actually plot a graph, and current is independent along the x-axis and mass is along the y-axis. So y-intercept here 0, then you will see that our graph will be a straight line, because this equation can be written as m is equal to BL over G times current I. So what we do have here, that our this M is along the y-axis, current is along the x-axis, this is a straight line, then BL over G, this is the gradient of this curve. So this actually the gradient delta M over delta I, this is going to be BL over G. L you know, G you know, B you can calculate. So it means that our BL over G is equal to delta M over delta I. So B is equal to this G would multiply over there, delta M G over delta I times L. So in this way, you can actually calculate magnetic flux density. So this is a very simple experiment. Here, you also understand that how we can develop a simple concept of an experiment to determine magnetic flux density of a bar magnet to test it. And then you also actually can understand here that how we perform experiment, how we take data, and how we actually plot, meaning that and we process the data to understand it. Very good. So with this understanding, then we can go ahead, and in this formula, we actually learn that actually with this equation of the force on a current carrying wire, we can actually can go to the formula F is equal to some charge, let's say small q here, then magnetic flux density times velocity of our charged particle. And this formula says that here the value of the sin theta is equal to 1, meaning theta is equal to 90 degree, meaning that this magnetic field and velocity of the charged particle are perpendicular to each other. Now let's think that if we put a charged particle in a magnetic field with this condition, what would happen? Here, let's say we have magnetic field within this area over here, and this cross indicates that the field is into the screen because we are looking at the cross. We are looking at the tail of our arrow. So these are the wings. So now what will happen? So here that let's say the charge particle actually entered from right side inside this magnetic field. This is the velocity vector. So if we are, let's say, at point number 1, what will happen? We need to first identify the direction of magnetic force. This force in this picture, it is FB. So I am also writing in this formula FB. So this FB we can determine using direction of this force. We can find using left hand rule. What the left hand rule is that the first finger towards the direction of magnetic field. Excuse me. So first finger is along the magnetic flux density, meaning magnetic field. So put your first finger of the left hand toward this screen, then the second finger. Second finger, we actually said that that is the direction of the current. Current means the flow of charged particles, meaning here in this formula, velocity vector. So our second finger is a velocity vector. Where the thumb is, you will find the thumb is along here, and you also observe here that magnetic force perpendicular to the velocity vector and also perpendicular to the magnetic field vector. Okay, now if this charged particle is, for example, at this point, point number 2 here, then what will happen? That now this so velocity vector is always a straight line because this is a vector. So now you can see again the first finger of your left hand towards the screen, second finger downwards, then the force will be perpendicular to the velocity vector again here. Okay, so at the third point you can again check that the force is along this direction over here, and at fourth point it is again towards actually here in this towards this point O, let's say. So at the end, what would you see? That this charged particle actually inside the magnetic field is moving in circular motion, is moving in circular motion in magnetic field. So what does this mean? that if we have a charge particle Q and moving with the velocity v, and it entered at 90 degree to the magnetic flux density b, then this charge particle will be moving in circle. And remember that here nothing is going to change. However, a force is working on this charge particle. What? It actually would not get extra energy. It is actually just moving in circular path. This magnetic field is just bending the direction, is just changing the direction of the charge particle, meaning that it is just bending the charge particle, and in the result the charge particle will be moving in circular motion. So here we understand that the charge particles move in a circular path inside the magnetic field. Very good. This is clear. And then we also actually observe that this magnetic field force will be always towards the center. So it means that this force FB is providing the centripetal force. The centripetal force mv square divided by the r. So this r is a radius of the circle. It is radius of the circle. V is the velocity. M, this is the mass of the charge particle. Okay, good. Very good. Now, what we can learn with this kind of observation, this kind of experiment. So, this force we can put from our first relation, that the charge, strength of magnetic field, velocity is equal to mass times velocity square divided by the radius of this circle. Now this velocity one actually gone with the one, we left with the one here. Now let's rearrange this equation to find this radius. So this r, it will go to the left side of the equation, and this factor qb will move toward the right. Then we get that mv over q times the strength of the magnetic field. Very good. So it means if, for example, we have the actual value of velocity, we have actual value of velocity of the charge particle, this magnetic flux density that we applied, so we would know also its value. Then what we can do, by actually measuring the radius of this circular path, radius of this circular path of the charge particle inside this magnetic field, we can actually find the mass over charge ratio, meaning that mass to charge ratio, or you can say charge to mass ratio, and this we also call it effective charge. This is effective charge with the units of coulomb per kilogram. So this is the effective charge of a charge particle. And there are many advantages of this phenomena of magnetic field, meaning that the force of the magnetic field on a moving charge particle, it can actually provide us uh, too much interesting information, that what we will discuss in detail in our next lecture. So for today, we keep our actually lecture up to this. So today what we learned that what the magnetic field is at the space around magnet, in which it actually in the other you could say the magnets can experience its force. And this magnetic field or magnetic force can be represented. It must be said that the magnetic field can be represented as the magnetic field lines. The strength of the magnetic field is proportional to the density of the magnetic field lines, meaning that if you have uh, a large number of magnetic lines over a cross-sectional area, that means the flux is higher. That means the magnetic flux density is higher. And the B is the magnetic flux density. Magnetic flux density. And this is actually equal to the flux over cross-sectional area. So that what we actually measure in the units of Tesla. That what we measure in the units of Tesla, and this actually the flux that we actually Baba. So is the flux and area, meter square. So then we also actually learn that if we have a conducting wire, current is passing through, then we can actually have a magnetic field around the wire, and that magnetic field is in a circular path around this current carrying wire. And this can be actually checked using the right hand rule. Right hand rule. In right hand rule, we have a two parameters, one curling, other straight. So that same we can apply to a coil where the current is actually curling and magnetic field will be a straight line, particularly inside the coil. And then we learned that the force on a current carrying wire by a magnetic field. Then we also did a very small experiment to measure the magnetic flux density. And then at the end, we actually uh, uh, did some calculations on this formula of the magnetic force. And we actually looked that it can also tell us the force on a moving charge particle inside the magnetic field. And then the most important was that if the angle is zero, meaning if the charge particle is parallel to the magnetic flux lines or at rest, then magnetic field is totally blind. So then magnetic field cannot see that charge particle to apply any force. And interestingly, that when charge particle enters in the magnetic field at a right angle, so it will actually get the centripetal force, meaning it will start moving in circle. That actually provides a lot of applications and very interesting information that what we are going to discuss in our next lecture. Hope you enjoyed the lecture. Thank you very much for listening carefully.